Hello, my name is Swetha Kurup. My ID number is 17007806, and I'm going to be presenting on the progress updates for my FYP project, which is the turbulence model study on convective heat transfer from a reactor. My supervisor is Dr. Afiq bin Mohammad Laziz. So let me start by going through the background of study or giving a brief introduction. So turbulence is the phenomena of random movement or motion of fluids. It is completely irregular in nature and often described as violent or sudden movement of fluids. So in order to better understand turbulence, several different mathematical models can be used, and oftentimes these mathematical models are used for the computational fluid dynamics simulation. So turbulence modeling using CFD is widely used in many different industries, including aerospace, automotive, chemical manufacturing, and many more, according to Davidson 2002. So in general, these models are generalized as the Navier-Stokes equations, but there are 7 different types of Navier-Stokes equations, and these include models such as the direct numerical simulation, which is known as the DNS model, but this model is often not used because of its high levels of computational power that is required, so it's not as feasible. Therefore, a more averaged form is used, which is known as the Reynolds averaged Navier-Stokes equation. And there are 2 alternatives to the RANS or Reynolds average Navier-Stokes equation, which is known as the SRS model, which is the scale revolving simulation, and the large eddy simulation LES model. But these methods are not as widely used as the RANS model because it is not much more expensive. But this project looks into the turbulence of air and the effects of natural cooling for an area with high temperature, such as a reactor. Therefore, it is also important to understand the properties of natural convection, which will be further discussed in the literature review section. Now moving on to the problem statement of the project. So heat loss, which is a natural phenomenon that occurs when heat is transferred via several methods, is oftentimes experienced by areas with high temperature. And oftentimes the type of heat loss that occurs are through convection, which is the natural convection or forced convection. So areas where there are high temperature, as mentioned, such as a reactor, are often subjected to this type of heat loss. And the type of flow that occurs within this area is turbulent flow. Therefore, different types of turbulence models have been investigated to identify which is the best model to determine the heat experienced in these areas from natural convection. So the comparative study for this particular area, as well as the most suitable type of turbulence model for this particular area, has yet to be thoroughly explored. Therefore, this project will compare all types of different turbulence models which have not been commonly used to be compared in the industry, as well as determine the most suitable one for this specific area. There are 2 main objectives of this project. Firstly, to investigate the most suitable model for the area experiencing heat from natural convection. And secondly, to validate all the experimental data obtained from other sources. Next, moving on to the literature review part of the project. In this project, the selected models to be compared are the Spallart-Almaraz 1 equation model, the standard K-epsilon model, the RNG K-epsilon model, the SST K-omega model, and the generalized K-omega or Gecko model. But before we move into those models, let's start with the generalized model, which is the RANS model. And as shown on the screen is the generalized equation. The Reynolds average Navier-Stokes or RANS model is the average version of the entire Navier-Stokes equation. Now, let's start by comparing the different models. The first model is the Spallart-Almaraz 1 equation model, and as shown on the screen, there is one equation for this model, and its main purpose is to solve the transport equation of the kinematic turbulent viscosity. However, this model can only be used for wall-bounded flows, and when used in other scenarios like free shear flows, it produces large errors. So the next model to be compared is the standard K-epsilon model. This model is widely used, and it has two equations as shown on the screen. The top equation represents the turbulent kinetic energy equation, and the bottom equation represents the dissipation, or known as epsilon, according to Launder and Spalding, 1974. So these equations help minimize the unknown and allow the equation to be applied to various different scenarios. But the one disadvantage that this model has, it's very sensitive towards pressure gradients, according to Mentor 1993. Another type of model under the K epsilon models is the RNG model. This model again has two equations and is used to understand turbulence with effect to its Reynolds number. So the RNG model is used to handle lower Reynolds number flows, and as you can see, the equation shows again the kinetic energy equation and the dissipation equation. So the next model to be compared is the SST-K omega model. This model is widely used because it is the combination of the Wilcox K omega model and the K epsilon models. So this model is less sensitive to flow outside of the boundary layers, which is according to the simulation manual under the SST-K omega turbulence models 2019. And this model shows again the turbulent kinetic energy equation and also the dissipation equation. Moving on to the last model to be compared is the generalized K omega or the Gecko model. And the generalized K omega model or the Gecko model is similar in terms to the K epsilon model in terms of its behavior. However, this model has one big advantage, is that it has 4 free parameters which can be adjusted according to whatever application required. So this method can be used without tuning. And in the slides, it shows the equations for the turbulent kinetic energy and the dissipation of this particular model. Now moving on to the last part of the literature review, which is under the natural convection. As stated earlier, this project deals with natural convection. So what is natural convection? Natural convection occurs when there are uneven temperatures and between the two fluids, and this causes the change in density between the fluids, which causes the flow of the fluids. And there are no external forces involved in this type of convection, such as pumps or fans, according to Zheng et al. 2021. So natural convection also varies according to the geometry of the area of the material. According to Balaji et al. 2021, the geometry, the temperature difference, as well as the medium of the fluids all affect as a controlling variable to natural convection. Besides this, natural convection's turbulence also depends on the Grashof value, as can be seen in the slide. So Grashof value here, the G represents the gravitational acceleration, the beta represents the coefficient of thermal expansion, the delta T represents the temperature difference, the L represents the height of the area, and V represents the kinematic viscosity. This value will affect the turbulence of natural convection. Now moving on to the proposed methodology. So for this part, there's going to be two parts of this project. Firstly, the designing the area itself, and secondly, the simulation. So firstly, for the designing part of this project, from the ANSYS workbench software, the fluid flow fluent is selected from the toolbox, as you can see on the slide. Then the geometry section is selected and a new geometry can be designed. To do the design, basically the first step to do is to sketch the design onto a plane and using the dimension tools, and also the dimensions can be selected and fixed, as well as the constraints can be identified. So once the sketch has been completed, the generate button can be selected and the geometry will be designed. So then going back to workbench, the mesh for this particular geometry has to be generated. So to do so, the mesh is selected and generated. And once the most accurate mesh has been identified and created, such as the skewerness has been reduced, then the simulation for this particular design can be started. So for the simulation part, going back to the Fluid Flow Fluent tab in Workbench, the solution is selected, and from Fluent, the model type can be selected. So all the different model types discussed earlier can be selected, and their variables are inputted, and other details for the material, such as in this case air, is identified as the fluid, so can be selected, and also the temperatures for this air can be inputted, and the contours are selected and set as temperature contours because we want to identify the temperature contours. And then next, the step time, the number of time steps, the max iterations, as well as other different parameters can be inputted, and then the calculation can be run. And once the calculation has been completed, in Workbench, under the Results tab, the details of the contours can be selected. So lastly, the temperature graphs produced from this simulation, as well as the contours animations, can be saved as an MP4 file. As shown in the picture here, this is an example of a simulation for one of the different types of models used. So in conclusion, for up till this point, for the progress update, there are different types of turbulence models, and they have been investigated and compared. And this will allow smoother comparisons when conducting the simulation later. The experimental data to be compared as well has been obtained, which will allow the data to be compared later and once the simulations have been completed. As for the theoretical part, the mathematical equations for these different models were compared, and also the concept of natural convection was explored further, as well as that different types of simulations were conducted to obtain the methodology for this project. Moving forward, more simulations related to this area can be conducted so that the experimental data can be compared, as well as that further research can be done on natural convection. With that, here are the references used for this project up till now. Thank you very much.